Good day, students. Today we're going to talk about X-ray diffraction, and why not? We're also going to talk about scanning electron microscopy, just for you guys. It is important for you to remember the definition of a crystal. So first of all, don't forget this definition of a crystal, which has to do with a unit cell that is being repeated. This is very important because this way you can know when you're talking about a crystal or an amorphous material. remember also that you have crystal systems and 14 Bravais lattices to classify your crystals. And this is when XRD is important to us. With X-ray diffraction, or XRD, we can analyze a sample and see whether it's crystalline or amorphous. We can know which crystal phases do we have, which crystalline compounds do we have, and more information. But first, let's talk about the electromagnetic spectrum. You also know by now that the wavelength can be different according to the radiation you're talking about. You can see visible radiation, but we cannot see the waves of radio coming to us, or even the gamma rays. We cannot see the gamma rays coming from the sun. X-rays show wave nature with the wavelength ranging from about 10 to 10 to the minus 3 nanometers. That is this range over here. But how can we produce X-ray in a laboratory? When a high voltage with several tens of kilovolts is applied between two electrodes, the high-speed electrons with sufficient kinetic energy drown out from the cathode, collide with the anode, and these electrons rapidly slow down and lose kinetic energy. Since these slowing down patterns vary with electrons, continuous X-rays with various wavelengths are generated. So this is what I was telling you about. We have an electrical circuit in which we have a resistance in which we apply a very high voltage, and this metal of here is going to produce us the electrons. This is an example of a diffractometer, the equipment that is used in XRD. A diffractometer is a precision instrument with two axes of independent rotation. This equipment enables us to obtain the intensity data of a diffracted X-ray beam as a function of an angle, so it is to satisfy Bragg's law under the condition of X-rays of unknown wavelength. The basic design of the diffractometer is illustrated in this figure. Three components we have: the X-ray source, which is this one, the sample holder, which is this, and the detector, of course, which is going to be moving in this angle, in these two angles, two theta. And we can see here the very important thing here is the same three things that I just showed you. The X-ray source, here it is. The sample holder, in here you put your specimen, and the detector that is going to be moving with the angles, okay? And also, you know that this experiment is ruled by the Bragg's law. This is the Bragg's law, as you know, as you already know, the Bragg's law, which is very useful in the case of wanting to get the interplanar distance of a lattice and even the parameters of a unit cell, as we have already done in some other classes. Crystallographic planes can also be indexed using a system developed by W.H. Miller, as you remember from previous classes, which helped us to determine a plane on a crystal. So you have the plane 001, the 110, the 100, the 111, etc., etc. Okay. All substances produce a characteristic diffraction pattern, X-ray diffraction discloses the presence of a substance as its existing form, not in terms of the constituting elements. This is the reason why graphite can be differentiated from diamond by the diffraction method, even though both consist of carbon. So if the graphite is made by carbon and the diamond is also made by carbon, we can differentiate both of these compounds by X-ray diffraction. That is one example in which we can apply. Some other applications in which you can find XRD is wanting to know the component of a seashell, for starters. Who would have imagined that a seashell is a crystalline material? That was made only for, and that was made only of carbonate calcium carbonate, sorry, here it is. So this is a seashell, and it is made of mainly calcium carbonate. Another application are the zeolites. The zeolites are porous materials with many different applications. For example, the ZSM5 is widely used in the petrochemical area for the cracking of hydrocarbons to produce different types of products, such as gasolines. You can also confirm when you have an amorphous material, when you have this type of diffractograms, this kind of belly over here. If you don't have any peaks, it means that you have an amorphous material. This is the diffractogram of an iron BCC, or a body center cubic, from a problem you have already solved. And the solution of the Bragg equation for each diffraction peak gives the corresponding interplanar spacing known as the spacing. So it doesn't matter which plane you use. If you use this plane or this, you will always get, by using the Bragg's law, you will always get the same D spacing data. This is a diffractogram for sodium chloride, your salt that you use in your tacos, in which you can see all the crystal planes that are characteristic of this salt. Okay, so every one of these are characteristics planes of the sodium chloride, as you can see here. Okay, and as you know, you can have different types of planes. Okay. And of course that the UTM has already made these experiments. Here are some of your partners. Here are some photos. Wait. Here are some photos of the day that we went to the Instituto de Metalurgia, sorry. I have to say it in Spanish because it's a Mexican institution. And these are some of the results. They analyzed the seashell that I showed you earlier in a fragment. So first they analyzed the whole fragment, sorry, of the seashell. Then later they crushed down the seashell and they analyzed the powder. So take a look at the different peaks that you can see in both of the fragment or the powder of the seashell. And this is a comparison between both of them. The red one is the compound that the software gave us, which is the aragonite, which is called calcium carbonate, okay? And now, let's talk about scanning electron microscopy, which is the second structural test that we can use. The SEM, or scanning electron microscopy, the SEM is used for observation of specimen surfaces. The SEM requires an electron optical system to produce an electron probe, a specimen stage to place the specimen, a secondary electron detector to collect secondary electrons, an image display unit, and an operation system to perform various operations. The inside of the electron optical system, it is important for you to know, and the specimen chamber also must be kept at a high vacuum of 10 to the minus 3 or 10 to the minus 4 pascals. It is very important that the microscope runs at vacuum, at high vacuum. The electron gun produces an electron beam. So here is the electron gun, which is only a filament of mostly tungsten. So the electron gun produces an electron beam. This is your electron beam. You have a beam, which is made of electrons. Placing a lens below the electron gun enables you to adjust the diameter of the electron beam. The objective lens are used for focusing. In general, the specimen is observed at a high magnification in an electron microscope. Thus, a specimen stage which stably supports the specimen and moves smoothly is required. The secondary electron detector is used for detecting the secondary electrons from the specimen. The output signals from the secondary electrons detector are amplified and then transferred to the display unit. And here you can see the zoom in here in the specimen holder. You have here the specimen, you will have it here, and the specimen can rotate it as you wish. You can go up, you can go down, you can go left, you can go right, you can tilt it. You can tilt all over here to see only a different angle, okay? So remember that the condenser lens are used to make this electron beam have a different diameter, okay? This is the secondary electron detector, and we're going to talk about also about this secondary electron. What are the secondary electrons? And the way that we're going to talk about this is why images are visible in SEM. And the reason is because of the interactions of electrons with the specimen. Since the SEM image appears as if you observe an object with the naked eye, you may intuitively understand the features of the object. To fully understand the contrast of the SEM image, you must understand the principle of the formation of the SEM image. When electrons enter the specimen, as you can see here, this is the incident electron beam that comes from the electron gun. And when the electrons enter the specimen, the electrons are scattered within the specimen and gradually lose their energy. Then they are absorbed in the specimen. So as you can see here, there are different types of electrons that comes after the electron beam hits the specimen, such as the X-rays, the backscatter electrons, the secondary electrons, and many others, like the Auger electrons, the transmitted electrons. These are the ones that are being used in the transmission electron microscopy, which we are not going to talk about. And to be very precise, the secondary electrons are used more to see the morphology. Once you are in a microscope, you can select whether you like to see the secondary electrons or you want to see a backscatter electrons, depending on which detector you have. So if you have a detector of secondary electrons, you will be able to see the morphology of your specimen. So secondary electrons, remember, are often used to see the morphology of your specimen. For instance, this is the morphology of a tungsten oxide crystal. Meanwhile, the backscatter electrons are sensitive to the composition of the specimen, such as this image, which contains two different types of crystals, copper and nickel, as you can see. And as you can see also, you can see the different types of gray, while the nickel, what the nickel is a little bit darker, the copper is a little bit lighter. So that is one way you can see the composition of your specimen with a microscope. Now we're going to talk about characteristic X-rays. As explained before, when the incident electrons enter a substance, various electrons and electromagnetic waves are emitted from the substance. Characteristic X-rays are one of them, and they're called like this because their energies or wavelengths are characteristic of individual elements. And this is why the characteristic X-rays are used for elemental analysis, that is to know what is the specimen made of. Here we have an analysis by EDS, or by the Energy Dispersive X-ray Spectrometer, or EDS. And this is used to analyze characteristic X-ray spectra by measuring the energies of the X-rays. In a few words, this technique will let you know of which element is made your specimen. In this case, it was a sample that was made of nickel and zirconium. Generally, the software will already show you which element is assigned to each energy of the characteristic X-ray. So this is the characteristic X-ray energy for nickel. This also represents nickel. And for example, you have a lower energy for the characteristic X-ray of zirconium. Okay? So this is one way you can know which elements are in your specimen. Very interesting also. And of course that the UTM was present on doing some of these experiments at the same Instituto de Metallurgia, I was going to say. Okay, so take a look at this. And this is when we went and we see this guy is the chief of the equipment, and he was explaining to the students all that I'm explaining to you right now. And this is the equipment. It's not very big, as you can see. The one that is bigger is the transmission electron microscope. And as you can see, they have a little periodic table of elements. Here is the controllers. These are the controllers. Here is where you can manipulate the lenses. Here are the specimens, and here is the detector. Here is the detector for making an analysis of EDS. This is an example of something that we took was of a galvanized wire. Then we can see the same galvanized wire with a little cut at the end. Another sample that was analyzed was annealed wire. You can see that the annealed wire can bend itself in 180 degrees without breaking, without showing any marks of breaking. Here we have a closer look at a cut at the annealed wire. It looks like some kind of clay, which was pretty easy to cut. And also we saw a rusty nail. A nail that was probably made of steel or some kind of steel or iron. And in here, we can see the difference between the rust and the clean nail. Here is a part of clean nail, and everything else is made of rust or oxide, as you may know. Here you can see also the magnification scale. So, so this is a scale of 500 micrometers. Okay, this is the voltage that was applied, 20 kilovolts, okay? The nail was made of some kind of steel, as I already told you, and so it was kind of hard to cut it, as you can see here. And proudly, the students from the UTM visit the Instituto de Metallurgia and made practices on the XRD and SEM. So if it wasn't for this COVID, I was planning for you guys to come here to the Instituto de Metallurgia, but what we're trying to see is if at least we can send some interesting samples to analyze. So I hope that this can be done. If not, I'm going to leave you another project, okay? Because these guys had to do some kind of report after they did this experiment. So this is everything for now. Thank you for watching and keep on studying.